Hello everyone, welcome for the third time in the week where we are talking about the vapor power cycles. Here over the previous two lectures we have already talked about the ideal Rankine cycles, its different variations, or I should say not variations, rather different factors that we may have to include in the ideal Rankine cycle to have more practical predictions, something like the isentropic efficiencies for the turbines and pumps, the possibility of having pressure drop in the boilers and turbines. Those factors we have discussed. Then in the previous lecture we have talked about different ways of improving the efficiency of the Rankine cycle just by changing the maximum pressure or maximum temperature or maybe the condenser pressure. And also we have discussed the option of reheating the steam, or I should say by breaking the turbine expansion into two stages with a reheat in between, quite similar to the Brayton cycle. So, that multi-stage expansion with reheating is one very efficient way of increasing the output from a turbine or from a Rankine cycle. The reheat Rankine cycle gives you higher power output, because here we are achieving the expansion in two stages, one at the high pressure stage from the boiler pressure level to the intermediate pressure level, and then the low pressure stage from the intermediate pressure level to the condenser pressure level. In some turbines we may have even two stage of reheating as well, where we may have two intermediate pressure levels. So, the net effect of increasing the number of reheating stage, or I should say the net effect of increasing the reheat portion in the turbine expansion is to have a net increase in the total power output that we can get from the cycle, because there will be increase in the turbine work output, but the work input requirement for the pump will remain virtually the same. And also we have already seen that the pump work input requirement is virtually negligible compared to the turbine output. So, the total output will increase, but of course, that will also be associated with an increase in the heat input requirement, because along with the primary heat, additional amount of heat input also will be required for the reheating part, and therefore, total heat input will also increase, and hence the Rankine reheat cycle, or I should say reheat Rankine cycle, gives you higher power output, but may not provide any increase in the efficiency. The efficiency may increase, efficiency may decrease, or may remain more or less the same depending upon the level of the intermediate pressure. So, in order to have an increase, or I should also add that the biggest advantage of having the reheating is of course on the turbine exit side. There will be significant increase in the exit quality of the at the turbine exit, and therefore, the problem of erosion in the later stages of turbine expansion can be eliminated completely. Now, in order to have higher work output as well as higher efficiency, we have to go for something known as a regeneration. I touched upon this one in the previous lecture. Here, as you can see, this is an ideal Rankine cycle without any reheating. Here the boiler input power, or I should say the boiler operation starts from this stage point 2 and finishes at this point number 3. So, this is your temperature T 2 and this is your temperature T 3. So, the boiler heat addition progresses over a very large temperature range from T 2 to T 3. There are several example problems we have already solved. You can check out any of the example problems from there. Like if we take something like, say, our cycle is operating with a maximum pressure of 150 MPa and the temperature at the turbine exit is 600 degrees Celsius, and the minimum temperature which should correspond to the condenser pressure may be something in the range of 30 degrees Celsius. Then the heat addition progresses over this y temperature range of 30 degrees Celsius to 600 degrees Celsius, which leads to significant lowering in the average temperature of heat addition, particularly because of this portion, which we can also call a feed water heating portion. The water coming from the condenser is often called the feed water. The pump which we are using for the stage 1 to 2 or for the process 1 to 2 is also called the feed water pump or boiler feed pump, because its objective is to feed the water back to the boiler. So, often we call it a boiler feed pump, in short BFP. Now, the stream coming out of the boiler feed pump, that being such a low temperature compared to the turbine inlet temperature, we have a significant lowering in the average temperature of heat addition, and therefore, to increase the net efficiency of this cycle, we have to find an way of increasing the temperature of this feed water from this T2 level to the saturation temperature level, which is this T2 prime, where this T2 prime is nothing but the saturation temperature corresponding to the boiler pressure, like in this example 150 MPa. If we can somehow achieve that, that is the water coming out of the boiler feed pump will enter the boiler not with temperature T2, rather with the saturation temperature corresponding to the boiler pressure, then the average temperature will not corresponding to heat addition will not correspond to the 630 degree Celsius, rather there will be significant increase in this 30 degree Celsius. I have forgotten the number, but corresponding to 150 megapascal, your saturation temperature will be in the range of 250 degree Celsius or even more than that. So, immediately there is a big jump in the temperature level in this boiler operation, and so there is an increase in the average temperature of heat addition. TA average increases, and accordingly the thermal efficiency will also increase. So, that is the idea of regeneration, that is to increase the efficiency of an ideal Rankine cycle by incorporating the regeneration, where the objective is to raise the temperature of the feed water coming out of the boiler feed pump from the T2 level to the saturation temperature corresponding to the boiler pressure. But how can we do that? You already have studied the Brayton cycle, and there we have seen that the exhaust gases that are going out after the turbine expansion, the heat remaining in that exhaust gas is generally used to raise the temperature of the air before it enters the combustor. But that kind of option we do not have in case of a Rankine cycle, because here nothing is going out in a way. The steam is it is a perfectly closed cycle, and the water or steam, whatever we may call the working substance, that is bound within the domain of these boundaries. So, the ideal way of achieving the regeneration is something like this, where the water coming out of this feed pump, this stage number 3, before it enters the boiler with stage number 4, it is allowed to pass through the casing of the turbine or through the outer surface of the turbine, and water as it passes through the turbine, while it goes through the expansion process, but that expansion is no more an isentropic expansion, rather during this process its temperature also decreases because of heat addition. So, its entropy decreases even if there is no frictional losses, but entropy will decrease, because you know that entropy of a substance can change by two ways. One is because of heat addition and other is because of irreversibilities. So, even when there are no irreversibilities because of a heat transfer, I should not say heat addition or rejection, because of any heat transfer the entropy of substance can change. Now, here in the turbine, the steam which is coming with state number 1, as that passes through the turbine, it loses heat to the feed water, thereby its entropy also reduces, because the direction of entropy transfer along with heat transfer is the same as the direction of the heat transfer. So, its entropy reduces, as shown on this diagram. The turbine expansion starts from this point number 1, and had there been no regeneration, it should have ended up somewhere here. But because of the presence of regeneration, its temperature and entropy both reduces. So, it ends up at some point 2. 2 is the point up to which you have this regeneration going on. After this point 2 to 2 prime, it is a normal turbine expansion, that is isentropic expansion, when it is not in vicinity of any kind of feed water. But the 1 to 2, that is the turbine expansion, can be divided into two parts. This 1 to 2, where we have the regeneration going on, that is heat is getting transferred to the feed water from the steam which is getting expanded in the turbine, and then from stage 2 to 2 prime, which is normal isentropic expansion. So, this is the most ideal way we can achieve the regeneration. The advantage of this can be we can get the idea from by looking at this TS diagram. If we take any cross section of this turbine where the regeneration is going on, that is between state 1 to 2, you can see both the feed water and the steam are more or less at the same temperature. There is infinitesimally small temperature difference between the two, and therefore, the heat transfer that is taking place from the steam in the turbine to the feed water, that is happening with infinitesimally small temperature difference. So, that can be viewed as a reversible heat transfer, and hence the cycle that we have drawn, that is allowing you reversible heat transfer, and hence it is a perfectly reversible cycle now. And as this is a perfectly reversible cycle, so its efficiency has to be equal to the Carnot cycle efficiency. That is the biggest advantage of this particular ideal cycle with regeneration, but practically this is not possible. One big problem is that look what is happening during the turbine expansion. As it is getting expanded, had it been an isentropic expansion something like this, of course, during the expansion it starts with a saturated vapor, but gradually it gets converted to a mixture, and during the regeneration part again it is getting converted to mixture, but the quality is decreasing very rapidly, and so the turbine towards the later stage, towards somewhere here, has to deal with very wet steam, which is always very much problematic. There will be significant amount of erosion which can't be sustained in practical operation. Another problem is, if we want to have this on the turbine, we will have to act as both as a turbine as well as a heat exchanger, which is again very difficult. We always want to have the turbine built in adiabatic mode, so that there is no heat loss, and now we are talking about making it a heat exchanger. So, that is also impractical, and therefore, this ideal cycle is not possible in practice. Rather, we have to think about some other way of achieving the regeneration, and to have that, what is done in practice, instead of allowing the feed water to pass through the casing of the turbine, small amount of steam is extracted from the turbine from during some part of its operation, and that steam is supplied to a feed water heater, where it exchanges heat with the feed water and thereby raising the temperature of the feed water. And this is the scheme that I am talking about. So, a small fraction, like if we talk as the initial mass of steam to be equal to 1 kg, then a small fraction of that, that is y kg, is taken out at some intermediate pressure level. So, from this is the boiler feed pump, from there with state 8 it is entering the feed water is entering your evaporator. Just look at the subsequent TS diagram. So, this is your state number 8, it is it is already at the boiler pressure. So, at the boiler pressure it is entering the evaporator, and then there it is getting superheated up to state number 1, which is this particular point. So, this 8 to 1, this entire thing is happening at the boiler pressure, where the feed water subcooled or compressed liquid is getting converted to superheated vapor. Then it is passing through the turbine, but instead of allowing the entire quantity of steam to pass through the turbine, at some intermediate pressure level at this 0.6, small fraction is taken out, and the remaining fraction, that 1 minus y fraction, is allowed to complete the expansion. Look at the diagram, this is the intermediate pressure that I am talking about, where a small quantity has been taken out, remaining portion is allowed to complete the expansion to reach stage number 2. Once it reaches stage number 2, then it passes to the condenser. So, that 1 minus y fraction gets condensed to reach state number 3 somewhere here. Now, that is allowed to pass through a pump, where it is its pressure is raised to that intermediate pressure level. So, here also we are talking about two pressure levels. This particular or I should not draw this way, this particular pressure line is your boiler pressure line, this pressure line is the intermediate pressure line, and this pressure line is the condenser pressure line. So, there are two pumps, the first pump, the pump number 1, this is raising the pressure from the condenser pressure level PC to that intermediate pressure level, and once it reaches to the intermediate pressure level, now we have a feed water heater, which is nothing but a mixing chamber kind of thing. The condensate that is coming from your pump number 1, and also that y kg of steam that you have extracted, often called the bleed steam, that is coming from the turbine, that is they are allowed to mix in the feed water heater, and therefore, it forms a mixture of temperature or state 7. This is the state. Ideally, in case of ideal reheating, the state of the working substance at this point will be of saturated liquid at that intermediate pressure level. That can be controlled by controlling this fraction y. That is, we want, in case of ideal regeneration, we want the magnitude of y to be such that state 7 correspond to the saturated liquid state at the intermediate pressure level. Now, we have the second pump where the pressure is raised from this intermediate pressure to the boiler pressure to have reach state number 8, which is subcooled liquid now, but at elevated pressure, and then it proceeds to the boiler operation. This is also the alternate way or practical way of doing regeneration. In practice, any thermal power stations working with steam will be having feed water heaters, where steam will, just as shown here, steam will be extracted and that steam will be used to raise the temperature of the feed water. You can see there are two pumps that we are talking about. Pump 1 is raising the pressure from PC to P intermediate, and pump 2 is raising it from intermediate pressure to the boiler pressure. Pump 1 is taking its input from the condenser, and therefore, it is often called the condensate extraction pump. Condensate extraction pump, or in short CEP, and the pump 2, as it is going to supply the feed water back to the boiler, is called the boiler feed pump, as I just mentioned, or in short BFP. So, in power stations commonly you will find both the pumps in operation. One is the condensate extraction pump, which operates at the lower pressure level because it takes its input from the condenser, which is at the vacuum pressure, and raises it to the pressure of the feed water, that is the intermediate pressure at which the feed water heater is operating, and also the steam has been extracted from the turbine. And the second pump, the boiler feed pump, is taking its input from the feed water and supplying it to the boiler pressure. So, if we want to see a very brief analysis of this entire thing, look at this diagram. Let me remove all these red lines to make it more clear. So, in the boiler, the amount of heat that you are adding is equal to H1 minus H8, and that heat has been added to the entire mass. So, that has been added to the entire mass, that is 1 kg. In the condenser, the change in enthalpy is H2 minus H3, but look, the condenser is not operating on the entire mass, rather it is operating only on 1 minus y fraction. So, though the change in enthalpy of the working medium is H2 minus H3, but it is operating on 1 minus y kg of condensate per unit mass of the working medium, and so while calculating the total heat load of the condenser or heat rejected in the condenser, we have to take into account this 1 minus y fraction. And what about the turbines? Now, there are two stages of turbine expansion you can see. In one stage, the high pressure turbine, the change in enthalpy, the high pressure part change in enthalpy is H1 minus H6, and here it is operating over the entire mass. However, on the low pressure stage, the change in enthalpy is H6 minus H2, but here this is happening over 1 minus y kg. So, if you want to have the total turbine output, you have to consider different mass flow rates for different turbines. And what about the pumps? So, WP for the first one, which is the condensate extraction pump, here the change in enthalpy is from H4 minus H3, or if we see, as we have seen, often we can write this one as V3 into P4, that is the P intermediate minus P3. But this entire thing is operating on 1 minus y kg of mass, because that blade stream has not been mixed with the fluid. But what about the second pump, which is the boiler feed pump? Here again the change in enthalpy is H8 minus H7, which can be written as V7 into P8 minus P7, that is P8 is boiler pressure, P7 is the intermediate pressure, and it is operating over the entire mass because the mixing has taken place, mixing between the remainder of the condensate and the blade stream, that has taken place. Similarly, if we want to write an energy balance for the feed water heater, what you can write? So, the feed water is receiving y kg of steam from the boiler at state 6. So, it is carrying energy y into H6, and it is also receiving 1 minus y fraction of condensate coming from the condensate extraction pump with state 4. So, it is H4. So, H6 and H4 are the two corresponding states, and what are the output? The output is H7, which is having the entire mass into picture. So, this is for the feed water heater that we are talking about, an energy balance for the feed water heater. And of course, here Y is the mass fraction, which we can write as the mass mass flow rate of this blade stream divided by the total mass flow rate m dot 1 or maybe any other state that also we can take. But this way that we have shown the feed water heating, that is only the theoretical aspect. Practically we can have two kinds of feed water heaters: open feed water heater, where we allow the condensate and the blade stream to mix with each other, thereby having a direct heat transfer, and also the closed feed water heater, where they flow in some shell and tube kind of heat exchanger, that is condensate flows through pipelines and the steam is allowed to flow outside of that pipelines on the shell side, and therefore, there is no direct mixing, that is called closed feed water heater. First, this is the open feed water heater. In case of an open feed water heater, just the scheme that we have seen in the previous slide, here the blade stream coming with the state 6 and the condensate coming at the state 2, they are allowed to mix with each other. So, here as I have shown, here if the mass here is 1, then y fraction is flowing through the state 6 and 1 minus y fraction is completing the expansion going from 6 to 7 in the second stage of the turbine expansion, or maybe the remainder of the turbine expansion. And then this y fraction, of course, we are talking about two stages of turbine expansion, but truly speaking it is a single turbine. Just to mention that there are different flow rates, we are referring as one high pressure stage and another low pressure stage, but it is not like reheating where we have two different turbines. In case of reheaters, we have two different turbines, but here we have the same turbine, but having different flow rates, lower flow rates I should say, on the later stage of expansion. So, this condensate having mass fraction of 1 minus y, then gets passes to the condenser, then through the condensate extraction pump in 1 to 2, this is your condensate extraction pump, and then we have the open feed water heater, which is nothing but a mixing chamber, and the exit state of the mixing chamber in case of ideal regeneration cycle is, as I have mentioned, is saturated liquid at the intermediate pressure. So, the magnitude of y has to be selected such that H3 is equal to Hf corresponding to this intermediate pressure or feed water heater pressure. Here the role of this condensate extraction pump is very important, because as we are going for direct mixing, therefore, both the blade stream and the condensate has to be at the same pressure. And again, after the mixing takes place, we have to raise the pressure to the boiler pressure level, and therefore, we need two different pumps. Quite often power stations may have more than one heaters, and each of the heaters requires a different pump in when we are going for open feed water heaters, because we have to achieve mixing of feed water and steam at the same pressure, and therefore, at each stage the temperature the pressure of the condensate that has to keep on increasing to the pressure of the corresponding blade stream. So, this is the open feed water heater. Open feed water heater allows direct mixing of the two fluids, therefore, it provides very efficient heat transfer. And also another big advantage that we get with open feed water heater is that the condenser, as we have already seen, the works at the vacuum pressure level, subatmospheric pressure. So, whatever precaution you may take, but practically it is always possible for that some amount of non-condensable gases from the atmosphere may leak into the condenser and get mixed with the condensate. Now, gases like oxygen and carbon dioxide, when that get mixed with the water, that can lead to significant amount of corrosion of the corresponding pipes, and therefore, it is mandatory to get those gases eliminated from your water stream, and that can be done very easily in this open feed water heater. In the open feed water heater, as we are talking about condensate, as we are talking about the condensate mixing with the blade stream to get a saturated liquid mixture. So, it is when this mixing process takes place, it is generally seen that all those non-condensable gases, they get separated from this mixture and gets liberated to the atmosphere, thereby giving this state 3 to be virtually free of all those condensates. That is why open feed water heater has a very important role to play, though as we are going to see closed feed water heater in the next slide, though power stations commonly go for closed feed water heaters, several of them, but there will be at least one open feed water heater primarily to achieve this de-aeration operation, that is to remove the non-condensable gases, and therefore, this open feed water heater is often also called a de-aerator, that is its purpose is to de-aerate the condensate. This is the open feed water heater. Now, we have a closed feed water heater. In case of a closed feed water heater, the condensate is allowed to flow through these tubes, and the steam which is coming from the turbine, extracted from the turbine, flows over the outer surface of these tubes, thereby getting condensed, and this blade stream and condensate are never coming in contact with each other. Now, this the condensate that is formed here in the closed feed water heater because of the condensation of the blade stream, that subsequently can be pumped to a mixing chamber, or it can be pumped back to the condenser as well, or there can be several closed feed water heaters. Quite often the condensate formed from the blade stream are just allowed to flow back to the lower side, to the feed water heater which is operating at the lower side. In that case, we do not need a second pump, we rather use something called a trap. Trap is an arrangement which operates on throttling. It allows the condensate formed in the closed feed water heater from the blade stream to throttle back to the lower pressure closed feed water heater. The condensate from the last feed water heater is allowed to flow back to the condenser. Look at the subsequent TS diagram. Here again if one fraction is coming, or 1 kg of mass is getting expanded in the turbine, y fraction of that has been extracted at 0.7, remaining 1 minus y fraction completes the turbine expansion and then passes to the condenser, then it passes to the condensate extraction pump also. So, this state 1 to 2 is also corresponding to 1 minus y fraction. Then we have the feed water heater, but as there is no direct mixing, so after the closed feed water heating, they are not going to be at the same temperature, rather they will be at the different temperature. Look at this, the state 2 goes to state 3, state 9. So, the condensate which is whose pressure has directly been raised to the boiler feed pump pressure, it is heated up to temperature 9, whereas the condensate, or the blade stream coming with state 7 loses its heat to form this saturated liquid at state number 3, from where it is pumped back to state number 4 to the boiler pressure level, and then we have a mixing chamber quite similar to an open feed water heater, where they mix with state 9 and state 4 to give this final state of 5, which then process to the boiler. So, this is what we have in case of a closed feed water heater. Remember, here the blade stream and the condensate are not coming in contact with each other, therefore, this heat transfer is less efficient compared to an open feed water heater, and also requires much more complicated arrangement, because we have to arrange for the shell and tube kind of configuration. We have to ensure that the steam is not getting leaked into the water stream. But the advantage is, here we do not need a separate pump for every feed water heater. Just look at the arrangement shown here, where we have several closed feed water heaters. We have 4 heaters, 3 of them are closed and 1 is open. look at the last one, the one operating with the highest pressure. The condensate, here it is receiving the steam extracted with the highest pressure from the turbine. So, that steam when that gets the condensed, then using this trap it is allowed to flow back to the previous feed water heater, which is at a slightly lower pressure, because it is using condensate at this pressure which is lower than the first one. So, here we do not need a separate pump. Now, this from the second closed feed water heater, this the condensate coming from the first one is allowed to mix with the condensate formed in the second one, and then both of them are allowed to flow through the second trap back to the open heater. In the open heater, we are supplying steam at even lower pressure level, and also the condensate that is coming from the downstream side, they are all allowed to mix with each other. See, it is an open feed water heater, so there everything is allowed to mix with each other, and once that mixing has taken place, then the final outcome is raised to the boiler pressure level using this boiler feed pump. This is your boiler feed pump, but we do not need separate pumps for the other two closed feed water heaters. So, only one pump is sufficient to take the load of all these closed feed water heaters, or to allow the liquid to flow through all the closed feed water heater finally to the boiler. And there is also another closed feed water heater below this open heater, which is receiving steam at the lowest pressure level, and here again the condensate formed is allowed to flow back to the condenser via this trap. So, we have again just two pumps, one is the condensate extraction pump and another is the boiler feed pump. Now, you may question that earlier also you had two pumps, but see how many heaters we have. Here we are showing 4 heaters, but still we are using just two pumps. Condensate extraction pump will always be required even if you do not have any feed water heating. The boiler feed pump is coming because of the presence of the open feed water heater. So, we need one condensate extraction pump, and then whatever may be the number of open feed water heaters, accordingly same number of boiler feed pumps or feed pumps that we may be needing. If there are no open feed water heater, then that condensate extraction pump alone is sufficient, because it is directly going to raise the pressure from the condenser pressure level to the boiler pressure level. But as I have mentioned, mainly to have this de-aeration operation, we often go for at least one open feed water heater. Modern power stations, you may often find that you have the condenser, then you have closed feed water heater 1, then closed feed water heater 2, then you have another closed feed water heater 3, we may have a fourth one also, 4. So, 3 to 4 stages of closed feed water heating. So, the steam coming from the condenser, that is allowed to flow through the CEP, condensate extraction pump. From there it flows to the closed feed water heater number 1, from there to the second one, from there to the third one, from there to the fourth one. From the fourth one now it goes to the aerator, de-aerator, that is an open feed water heater. After the open feed water heater, now we need another pump, which is your boiler feed pump. So, from this condensate extraction pump outlet till the inlet to the boiler feed pump, the entire line is operating at that intermediate pressure level, which is the pressure of the de-aerator. Now, from after the boiler feed pump, then again we may have several closed type feed water heater. So, we may have closed feed water heater number 5, then we may have closed feed water heater number 6, quite often we have a 7th one also, heater 7, and then finally it is going to the boiler. That means, we are having, as shown in this diagram, which is very common in several Indian steam based power stations, we have 8 stages of feed water heating, 7 of them are closed feed water heaters and one is open feed water heater, which is a de-aerator. Now, the de-aerator and the first 4 stages of the closed feed water heating are operating at the intermediate pressure level or the de-aerator pressure level, and the final 3 feed water heaters, closed feed water heaters plus the boiler is operating at the boiler pressure level. For each of these feed water heaters, the condensate formed from the blade stream are fed back to the lower one through the trap. like the condensate formed in the closed feed water heater number 4, that using a trap is fed back to the third one, where it gets mixed with the condensate formed here. So, which is again via a trap is fed back to the second one, where it gets mixed with the condensate formed by the blade stream coming directly to this second feed water heater. So, then we may have another trap which is taking the condensate back to the feed water heater number 1, which combines all these feed waters, or sorry, all these condensates, and also mixes that with the condensate of the blade stream coming directly to this, and finally this one via a trap goes back to the condenser, or I should have drawn like this, goes to the condenser. Similarly, the condensate that is formed in the closed feed water number 7, that is allowed to flow back to the one at number 6 through a trap, where it gets mixed with the blade stream or the condensate of the blade stream coming directly to the 6. So, that condensate, that mixture is allowed to flow back to the number 5 through another trap, where that get mixed with the condensate formed individually here. Finally, that through another trap is fed back to the deaerator. So, for each of the closed feed water heaters, we are having a trap which is taking the condensate back to the lower side, but we do not need additional pumps for any one of them. That is one big advantage of the closed feed water heaters, and that is the primary reason that we go for the closed feed water heaters. Also, another big advantage of closed feed water heating can be that we can, as they are closed in nature, so we can have any kind of orientation. They are generally much smaller in size compared to the open feed water heater, and we can feed them anywhere in the orientation of the power stations, because they are generally much more compact. Let us solve one numerical problem to see the effect of this regeneration. Just read the problem carefully. We are talking about a steam power plant operating on an ideal regenerative Rankine cycle with one feed water heater, just a single feed water heater we have here. Steam enters the turbine at 15 megapascal and 600 degrees Celsius and condensed in the condenser at 10 kilopascal. Some steam leaves the turbine at a pressure of 1.2 megapascal and enters the open feed water heater. So, we are talking about an open feed water heater, just a single feed water heater, and that is of open type, and this 1.2 MPa is the intermediate pressure. So, here we can note the I will note down the things later on. Let us read the problem or complete the problem. Determine the fraction, we have to determine the fraction of the steam extracted from the turbine and the thermal efficiency of the plant. So, this is the diagram of the plant. Here we have the boiler pressure to be equal to 15 megapascal, condenser pressure to be equal to 10 kilopascal, and the intermediate pressure, which is the pressure corresponding to the open feed water heater or the deaerator, is 1.2 megapascal. So, look at the diagram, it is very similar to the open feed water heater diagram that we have seen earlier. So, steam coming from the boiler with stage number 5 with 15 megapascal and 600 degrees Celsius is fed to the turbine, where it gets expanded. At point 6, some amount of steam has been extracted. Let us assume this mass of steam to be equal to y. Here the total mass is 1, then 1 minus y fraction continues to point number 7, where it goes through the condenser. Then we have this condensate extraction pump as the pump number 1, which raises the pressure from 10 kilopascal to 1.2 megapascal, which is the pressure of this open feed water heater. So, this condensate at 1.2 megapascal pressure and blade stream coming with 1.2 megapascal pressure are allowed to mix in this open feed water heater. So, this condensate is coming with mass fraction of 1 minus y, and they form a mixture at the same pressure of 1.2 megapascal. Here now the mass is back to 1, where we have the boiler feed pump, which increases the pressure from this 1.2 megapascal to 15 megapascal and feeds it back to the boiler. Now, here we are talking about an ideal regenerative Rankine cycle. So, these are the things that can be assumed. Isentropic efficiencies of turbine and pumps are unity, because nothing is mentioned, and we also are talking about an ideal cycle. So, they must be having isentropic expansion or compression. No pressure drop in the boiler, condenser and feed water heaters. So, only 3 pressure levels to be considered, these 3 only, we do not have to bother about any other pressure level. and also states at the exit of condenser and feed water heater are of saturated liquid. That is important, that is associated only with the ideal cycle. In practical cycle they may be subcooled or they may be very low quality mixture as well. So, we have to work out the states. So, state number 1, in state number 1 we have P1 to be equal to 15 megapascal, T1 equal to 600 degree Celsius. So, we have to make use of our tables. Sorry, I have noted it wrong. It is our state number 5. So, for state number 5 we have H5 to be equal to 3583.1. I have already noted the values from the tables, and S5 you know that we need the entropy because we are talking about isentropic expansion. So, it will be coming as 6.6796, 6.6796 kg. But point 5 we shall be coming back later on. Let us focus on point number 1. Point number 1 has a pressure of 10 kilopascal and quality equal to 0 because we are talking about saturated liquid. Then your H1 should be equal to HF corresponding to P1, which I have noted to be 191.81 kilojoule per kg, and specific volume V1 should be equal to Vf corresponding to P1, which is 0.00101 meter cube per kg. So, we know point number 1. Then in the pump it is raised to point number 2, and therefore, for point number 2 we know that pressure is 1.2 megapascal, and this being isentropic expansion is to equal to S1. But for pumps, as they deal with liquids, so we know that we do not have to think about this isentropic expansion or is to equal to S1, rather we can directly calculate the pump work. So, W pump for this condensate extraction pump should be equal to V1 into P2 minus P1, and we have already got all the values. So, this will be coming as 1.2 kilojoule per kg, and if we are looking to have the rate of this pump, the work input rate, then we have to multiply this as 1 minus y into mass flow rate into this one, where the role of this 1 minus y fraction will come into play. Presently we do not need this, so I am not bothering about the 1 minus y fraction. Once we know this, so using this we can calculate H2 to be equal to H1 plus WP1. Here 1 and 2 both correspond to the same mass fraction, so you can directly go for the addition, and it is 191.81 plus 1.2, so it is coming as 193.01 kilojoule per kg. This is the cycle of the TS diagram for the same cycle. The state 1 where we have the mass of 1, here y fraction has been taken out, this is 1 minus y fraction, this condenser also is operated over 1 minus y fraction. So, we have evaluated process 1 to 2. Now, look at state number 3. For state number 3, we know that the pressure is the pressure of the open feed water heater. So, it is 1.2 megapascal, and as it is an ideal cycle, so X3 also will be equal to 0. So, we can easily calculate H3 to be equal to HF corresponding to P3. The value is 798.33 kilojoule per kg, and V3 will be equal to Vf corresponding to P3. So, it comes as 0.01138 meter cube per kg. Though we are taking 6 digits after the decimal point, practically it is not required. And also look that in the previous case V1, it was also 0.001, and despite the increase in pressure from 10 kilopascal to 1.2 megapascal, such a large increase, it is still more or less the same value. So, there is hardly any change in the specific volume, that is logical also. Liquid water is incompressible, that is its specific volume or density is independent of pressure, which we can see here. So, we know point number 3 now. So, we have to now identify the point number 4. Point number 4 corresponds to the boiler pressure level, which is 15 megapascal, and also this being isentropic expansion. So, S4 equal to S3, but again we are talking about the pumping operation performed on saturated liquid water or compressed liquid water. So, we do not need to make use of this S4 equal to S3, rather we can directly calculate the pump work for this two to be equal to V3 into P4 minus P3. P3 is the intermediate pressure of 1.2 megapascal, P4 is the boiler pressure of 15 megapascal, and this work is coming to be 15.7 kilojoule per kg. So, it is higher compared to the previous case. For the first pump we had 1.2 sorry, our work was 1.2 kilojoule per kg, it is 15.7, but still quite small compared to the turbine work output that we can expect. So, using this we can calculate H4 to be equal to H3 plus WP2. So, coming as 814.03 kilojoule per kg. Remember, this second pump operation has been done on the entire mass of 1, whereas the first pump operation was done on only that 1 minus y fraction. So, if you want to calculate the total power input required, then we have to multiply them by separate mass flow rates. So, we know now point number 4. So, 1, 2, 3, 4 are known to us, point 5 is also known to us. So, we can easily calculate QB, the heat input required in the boiler, which is H5 minus H4, and that will be coming as 2769.1 kilojoule per kg. Again, point 4 and point 5 corresponds to the same mass flow rate, which is 1. So, we can directly perform this operation without bothering about the mass flow rates. But we have to talk about the feed water heating process and also the turbine side. So, we have to identify point number 6 in that case. Look at point number 6. What informations are known to us? For point 6, we know that the pressure is that of intermediate pressure, that is 1.2 megapascal, and this being isentropic expansion, S6 should be equal to S5. So, S5 we have noted in the previous slide, which is this number. So, using this we know the value of S5 now, or sorry, we know the value of S6 now, and if your S6 is greater than Sg corresponding to P6, which is coming in this case, then you know that it is superheated vapor as shown in the diagram. So, we have to identify its temperature by using the superheated vapor table corresponding to 1.2 megapascal, and in this particular case I have directly got the number. Your T6 will be coming approximately 218.4 degree Celsius, which gives you H6 to be equal to 2860.2 kilojoule per kg. And what about state number 7? State number 7, the pressure is the condenser pressure, which is 10 kilopascal, and S7 should be equal to S5 because this is isentropic expansion. If you combine this, you will find that this S7 is coming in between SF corresponding to the condenser pressure and Sg corresponding to the condenser pressure. So, it is a mixture. Calculating this, we get x at 0.7 to be equal to 0.8041, and putting this number, then H7 is coming to be 2115.3 kilojoule per kg. So, now we have information about all the possible states. So, how can we calculate the value of this y fraction? Of course, we can perform an energy balance over the feed water heater. So, over the feed water heater, if we perform an energy balance, then we can easily write y into H6 plus 1 minus y. Just look at the feed water heater. It is receiving blade stream of mass fraction y with state 6 and condensate with mass fraction 1 minus y with state 2 and forming mass state 3 with the complete mass. So, it will be 1 minus y into H2 to form H3, and if you calculate this, we already know the value of H6, H2 and H3, all are there on the slides. So, putting this, your H will be coming as 0.227. So, 22.7% of steam has been extracted from this from the turbine to be supplied to the boiler feed pump, or sorry, to the feed water heater. And how much is the condensate load? Remember, condenser works on 1 minus y mass fraction. So, it is 1 minus y into H7 minus H1. Putting this, your value will be coming as 1486.9 kilojoule per kg. So, the thermal efficiency for this plant is equal to 1 minus QC upon QB to be equal to 46.3%. Just check in the previous slide, or sorry, just check the lecture of the previous week. There we have solved a problem with similar parameters, but without regeneration. There our efficiency was something in the range of 43%. Now, as we have gone for the regeneration, our efficiency has increased to 46.3%. Of course, we have extracted some steam from the turbine, and therefore, the net power output from the turbine will be lower. We have not calculated this, but the WT you can easily calculate as H5 minus H6 plus 1 minus y into H6 minus H7. I do not have the calculated value. If you calculate, I guess the turbine work will be coming to be slightly lower than what we got in the previous case, but the amount of energy supplied in the boiler, this particular number, that has also come down very significantly, just compare with the previous problem. That has led to an increase in the overall thermal efficiency of this plant. So, this is an example of how to solve a problem involving feed water heater. I am going to finish up giving you another exercise. I am not going to solve this problem, I am leaving it to you to try on your own. I shall be solving this one in the next class. Also, one additional information, this particular problem is a solved example in the book of Sengel and Bowles. Please try to solve this one on your own without looking into the book. And also before you start going to the next lecture, where I am going to solve this one step by step. Just read this problem. Here we are talking about a steam power plant operating on an ideal regenerative Rankine cycle with one open feed water heater, one closed feed water heater and one reheater. So, we are talking about a reheat regeneration cycle. We have reheater and also regeneration, plus there are two feed water heaters, one open type and one closed type. This is the cycle diagram for this. So, the steam that is coming to the turbine expansion has been divided into two parts, the high pressure turbine from where steam enters the high pressure turbine is state 9 at 15 megapascal and 600 degree Celsius, and then it is expanded to some intermediate pressure up to state 2, then it passes through the stage of reheating and it goes back to the low pressure turbine. Let us continue reading the problem. It is condensed to the condenser pressure at 10 kilopascal. So, this 10 kilopascal is the final pressure at the exit of the low pressure turbine and also in the condenser. Some steam is extracted from the high pressure turbine at 4 megapascal for the closed feed water heater, and the remaining steam is reheated at the same pressure to 600 degree Celsius. So, the 4 megapascal is the pressure at the exit of the high pressure turbine, and the blade steam for the closed feed water heater is also taken from the same line. That is, here the steam we are not extracting directly from the turbine, rather we are extracting it before this after the steam comes out of the high pressure turbine and before it enters the reheater. In between you are taking this blade steam, a small fraction y at this 4 megapascal pressure. Then the remaining fraction, which is 1 minus y, that is reheated back to that 600 degree Celsius and supplied to the low pressure turbine. The extracted steam is completely condensed in the feed water heater, following which it is pumped to 15 megapascal before allowing it to mix with the feed water at the same pressure. So, it is a closed feed water heater. So, it is forming condensate. This condensate is pumped using this particular pump back to the boiler pressure, where it is mixed with the stream coming from the closed feed water heater in this mixing chamber at the same pressure of 15 megapascal. Blade stream for the open feed water, it is extracted from the low pressure turbine at 0.5 megapascal. So, from low pressure turbine we have this blade line at 0.5 megapascal, it is coming and getting supplied to this open feed water heater, and the condenser pressure is 10 kilopascal. So, here another Z fraction has been taken out. So, 1 minus Y fraction, initially it was 1 which passes through the boiler and the high pressure turbine, then we take Y fraction out to supply to the closed feed water heater, remaining 1 minus Y fraction is going to the low pressure turbine. From there Z fraction we are taking for the open feed water heater, and 1 minus Y minus Z fraction completes the remainder of the expansion, and that is the same fraction that goes to the condenser. So, we have 3 pumps to be talked about here. There is the first pump which raises the pressure from 10 kilopascal to the pressure of the open feed water heater, which is 0.5 megapascal. The mixture from this open feed water heater is pumped to the pressure of that 15 megapascal, the boiler pressure, when it will be passing to the closed feed water heater and then to the mixing chamber. And we are not using any trap here, rather we are having a third pump which is pumping the condensate in the closed feed water heater to the mixing chamber. Instead of this, we could have easily used a trap to direct this condensate at 6 back to the open feed water heater, thereby you could have saved this third pump, and we also never required this mixing chamber. But in this problem they are using this third pump, and so we have a mixing chamber as well, but no trap. So, try to solve this problem on your own. You already know how to calculate. Remember, you are talking about an ideal reheat regenerative Rankine cycle. So, the isentropic efficiencies for the condenser and for the both stages of turbine and all the 3 pumps, that is 1. There is no pressure loss in the boiler, in the condenser, and also in the mixing chamber, and in all the 2 and in both the feed water heaters, no pressure losses. And also the exit state 1, and also the exit state for this open feed water heater, that is state number 3, that will be of saturated liquid corresponding to that particular pressure level. That is, your point number 1 will be having a pressure of 10 kilopascal and its quality will be 0 because it is saturated liquid. Similarly, for stage number 3, P3 will be the pressure of this open feed water heater, which is 0.5 megapascal, and it is also saturated liquid, so X3 equal to 0. Other informations are all given. Try to solve this problem on your own before starting the next lecture or before looking into the book. So, today we have talked about the regenerative Rankine cycles. We have seen how it can increase the efficiency. We have discussed from theoretical point of view and also through the numerical example. A regeneration can be achieved with the help of either open feed water heater or closed feed water heaters. Practical cycles or practical power stations generally have both of these kinds, generally only one open feed water heater and several closed type feed water heaters. So, that takes us to the end of today's lecture. In the next lecture we shall be finishing the topic of regeneration, where I shall be solving the problem that I have given here, and then a few other aspects, a few other kinds of vapor power cycles I would like to discuss. Thank you.